Hey guys, welcome back to Pop-em-Up Chem. And now that we've done the basics of functional groups in general, we're going to take kind of a slight deep dive over the next couple of lessons on some specific functional groups. And we're going to start that with alkanes. So let's get into it. So we're going to look at the two main different types of reactions that alkanes undergo and evaluate how CFCs pose a threat to the ozone layer towards the end of the lesson. But just to get started, pause the video and try this little refresh question to keep your functional groups in mind for this lesson. So hopefully when you were looking at this molecule, you saw this classic benzene ring on the left-hand side and the alcohol group attached to the benzene ring. And here we see the ester bond. So that ester C double bond O with the two carbon chains either side. But in this lesson, we're mainly going to be looking at alkanes, and we are going to look at combustion, which we'll be familiar with, and free radical substitution. So combustion obviously comes in two types. We've got complete combustion, where we react a compound with excess oxygen, forming carbon dioxide and water. And we also have incomplete combustion, where we have an insufficient amount of oxygen, so we form carbon monoxide, water, and carbon solid, soot. Now, the exact proportions of which these are made will vary depending on the amount of oxygen that is present. So this equation here is just an example. It could depend on the conditions if there was more or less oxygen present, but that is generally incomplete. So we're going to look at what makes a good fuel, and we're going to use table 11 and 13 in the data booklet to help us describe what makes a good fuel and why alkanes are good fuels. So a good fuel needs to be energy dense, it needs to be safe, obviously we're still going to burn it, but just generally safe, and it also needs to be clean burning, i.e. needs to be easy to complete combust. So let's take two examples of methane and octane in this table, and the values that are given to us are the enthalpies of combustion given to us in kilojoules per mole. However, we want to divide that by the molecular mass, and the reason is we want to find how energy dense they are per gram, because as a fuel they'll be used that way. So when we do this, we find that methane has a value of 55.7 kilojoules per gram and octane has 50 kilojoules per gram. So why is octane used as a fuel instead of methane? Well, that comes down to the safety. If we have a look here, we see these are all gases, and we see from pentane up, we have liquids. Now, dealing with a liquid is a lot easier than dealing with a gas. If you're trying to fill your car up at a station, having a liquid is a lot less dangerous for a normal person to use, and therefore octane is preferred. So why do we see this trend then? Well, if we draw these molecules out, what do we end up seeing? Well, this is where we have a look at our bond enthalpies. So if we have a look at methane, which is on the left-hand side, and we look at the bond energies, we see we have 4 CH bonds, which have a bond enthalpy of 414. So 4 CH bonds and 0 CC bonds. In octane, we have 7 CC bonds and we have 18 CH bonds. So because the CH bonds are higher in energy, that means the higher proportion of CH bonds, the higher the energy density. So as the chain gets longer, we reduce the energy density of alkanes. So combustion isn't the only reaction they undergo, however. They also undergo free radical substitution. So for this, we need a halogen and we need ultraviolet light. This will allow us to produce free radicals and substitute one of the hydrogens on the alkane for whichever halogen we've chosen to use. So what's a free radical then? So all a free radical is any species which contains an unpaired electron. If we take the example of Cl2, which we're used to drawing with one covalent bond to two chlorine atoms, we see that we have 8 electrons around each with a shared. Now, a radical is one that just has that unpaired electron. It has not yet or has recently been broken away from that covalent bond, and so we have this very reactive unpaired electron. These reactive species can undergo what we call chain reactions that happen in 3 steps. That's initiation, propagation, and termination. So it's kind of like any relationship, really. It starts, it carries on, and then unfortunately it ends. One of the unique and potentially annoying things about these reactions is all of the stages can influence the other stages, and so we can end up with a mixture and can't be sure of the product that we're producing. So let's take a deep dive on what these actually look like. But first, I wanted to make a couple of notes on reaction mechanisms, as these are going to be new to most of you. So a few rules we can follow to help us through this unit and beyond. Firstly, let's deal with the infamous curly arrow. So arrows in organic chemistry denote the movement of electrons, the half-headed arrow showing the movement of 1 electron and the whole-headed arrow showing the movement of 2 electrons. You always write the negative charge moving towards the positive. We never write this ion is moving. We always draw the movement of electrons. So remember that the arrows show the movement of electrons from one area to another. So let's take a look at the breaking of this bond here. So what is this showing? Well, this is showing that we have 2 electrons in the bond, and one of them is going to jump off and sit on one chlorine atom, and one of them is going to jump off and sit on the other chlorine atom, which is going to leave us with 2 of these chlorine radicals. And that's what we call a homolytic split, because homo means same, so each atom got the same number of electrons. Now, a heterolytic split is where both of the electrons from the covalent bond move to one chlorine atom, in this case. This would produce 2 different species. This one in the blue would have lost an electron, so it's going to be Cl+, and the one in the green is going to have gained an electron, so we'll have a full outer shell and will be Cl-. So you'll notice in drawing these, we've followed the rules that the arrows always start at the electron source and end at the what we call the electron sink. And we're not breaking the octet rule where possible. We're maintaining what we would call normal Lewis structures. And the whole purpose of this is to help us describe what's actually going on in a reaction. So let's turn our attention to the 3 stages of a free radical substitution reaction then. So we said the first stage was initiation. So I've got the overall reaction here. However, that is not going to be a good description of each individual stage. The first stage, we said we need a halogen and we need some UV light, which is going to produce 2 chlorine radicals by the mechanism we've already described of the homolytic break of the Cl-Cl bond. That is going from 0 radicals on the left-hand side of our reaction to 2 radicals on the right-hand side of the reaction. And it's important you take note of this because we're initiating. We're going from 0 to 2 free radicals. An initiation is always going to be characterized by this breaking of the halogen covalent bond into 2 halogen free radicals. But what about propagation? Well, in the propagation step, there are more possibilities for reactions. So from step 1, we now have some Cl radicals present, but we also have the reactants of the reaction. So let's give an example of a propagation step. Here we can take that CH4, and that will react with the Cl radical, forming CH3 radical and HCl. So you'll see on the left-hand side, we have one radical, and on the right-hand side, we have one radical, hence propagation, the continuation. Now, you do not need to know the mechanism for this reaction, but we can use our new rules to showcase them and get us more used to seeing these. So we have the CH4, and we have our Cl radical. Now remember, we're drawing a half arrow, and that is going to form a bond with the hydrogen here, and then the leftover electron in that CH bond is going to jump onto that carbon, and we're going to end up with the CH3 radical. So the radical has been passed on. But that's not the only step that can happen in a propagation. In a propagation reaction, this radical that has been formed can also become a propagator and start reacting with things that are in the solution. Remember, it's all a mixture, it's all together. All of these steps are happening alongside each other. So it might react with some Cl2. And in that case, we would end up with CH3 radical plus Cl2 goes to CH3Cl, which is actually one of the products that we want, plus Cl radical. And here you can see we can propose another mechanism for that. Again, we're going to use our half arrow is going to try and form a bond with the chlorine. One of the electrons from the chlorine bond is going to join with that, and then one electron is going to join onto the lone chlorine, forming that chlorine radical. Again, one radical on the left-hand side, one radical on the right-hand side, indicating again that propagation. Indeed, products made in the termination step may also come back and be used in propagation. So there are actually further reactions that can happen that we're not including here. So let's have a look at some termination reactions. Well, you guessed it, now we're going to end up with no radicals. Now we have all of the products that we've made so far, but the most simple termination reaction is the exact inverse of the initiation reaction, which is just forming Cl2 from the two Cl radicals. However, from the previous steps, we've got a lot of stuff going on in this solution now. So we definitely have 0 radicals left, but there are more than one ways to get 0 radicals in this case. We could also have CH3 plus Cl radical, which is going to form the product that is in the actual overall reaction anyway. So the product is made both here and in the propagation step. We also have the Cl3 radicals could react with themselves, forming C2H6. And indeed, this C2H6 itself could go back into the propagation step and then further be made into a C2H5 radical, and so on and so forth. Hence, the mixture is a problem because we don't know the exact composition of the products of this reaction when we do carry it out. So I know this can be a lot, so let's summarize. We've got an overall reaction and we have an initiation step, which goes from 0 radicals to 2 radicals. An example of this is Cl2 to 2Cl. We then have propagation steps in which one radical forms one further radical. This may be something like Cl plus CH4 goes to CH3 radical plus HCl, or it could be something like CH3 radical plus Cl2 goes to CH3Cl plus Cl radical. Indeed, as I've mentioned before, we can have longer chains formed when this reaction occurs with products from the termination reaction. So talking of termination reactions, there is a few examples where we're going from 2 to 0 radicals, the most simple being the inverse of the initiation step, which is 2 Cl radicals going to Cl2. There is the Cl radical with the CH3 radical, forming again our product, and the 2 alkane radicals forming together. And it's this further longer chained alkane that can then participate again in further propagation reactions. Okay, so let's get you trying some questions then. Starting off nice and simply, define a free radical. Pause the video to give yourself some time. Pop 'em up! Indeed, it is a species with an unpaired electron. Okay, so next I'd like you to propose an initiation step for the free radical substitution between hexane and bromine. This doesn't have to be a reaction mechanism, it just has to be the balanced equation that you would expect for this. Pause the video to give yourself a moment for that. Pop 'em up! Okay, so we've got an initiation reaction. So I'm going to write the overall equation out just so we don't get confused. But if we're doing an initiation reaction, then we know we're going to have 0 radicals at the beginning and 2 at the end. So the classic here is Br2 goes to 2 Br radicals. Okay, so try the same reaction propagation step then. Just one will do. Pause the video. Pop 'em up! So if we put in the overall equation, there are a couple of options you could have had for a propagation step. You could have had hexane reacts with the bromine radical to make the kind of hexane radical. And you could have also had that hexane radical reacting with the Br2 forming the bromohexane and the bromine radical. You could have even had that same reaction, but with a C12 chain if you'd included things that were made in the termination steps to be used in the propagation step. Okay, one last one then. For the same reaction, I want you to propose a termination step. Pause the video, give yourself a moment. Pop 'em up! Once again, if we put the overall equation in, you had 3 options here. Remember, we're always going from 2 radicals to none. So we can have the very simple, almost anti-initiation step of the bromine radicals reacting with each other. We can also have the C6H13 radical reacting with the bromine radical to form the bromohexane product. And we can have 2 C6H13 radicals reacting together to form C12H26. Okay, so where does the ozone layer fit into all of this? Well, as we looked at in Unit 4, ozone is an allotrope of oxygen. It's O3 and it has a bond order of 1.5 on both sides. It's harmful and unstable at sea level, but in the upper atmosphere, it helps filter UV radiation from hitting the Earth's surface through a process called the Chapman cycle. In this process, oxygen reacts with free oxygen radicals to form the ozone, and the ozone itself is struck by UV radiation, which causes the breakup of the molecule into O2 and oxygen radicals. These 2 reactions respectively represent the natural formation of ozone and the natural destruction of ozone, an ongoing cycle. This process acts as a protective barrier to the Earth against ozone, which, if we did not have the ozone layer, life on Earth would look incredibly different, even if it could exist at all with the intense radiation that would cause genetic deformations and potentially not allow the kind of natural selection that allowed the development of higher animals on the planet. This is where CFCs and HFCs come in. These are fully halogenated hydrocarbons, usually derived from methane, ethane, and propane, such as dichlorofluoromethane, being a simple and common example. And these are very useful compounds. They're used as refrigerants, as propellants, as solvents. So that's in things like deodorant, they can act as a propellant. And they were found to have low toxicity, reactivity, and flammability when they were found. So, of course, this is tick, 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 a miracle. We can use them. Fantastic. Amazing. However, it didn't quite work out like that. As with a lot of things, the long-term consequences were unseen. Indeed, although unreactive on the ground, in the upper atmosphere, CFCs are exposed to UV radiation. That UV radiation causes the homolytic breaking of the C-Cl bond, and that C-Cl bond homolytic break leaves us with Cl radicals. Cl radicals can react with ozone and disrupt the Chapman cycle. They react with ozone to form ClO radicals with oxygen, and that is bad enough as it is, to be honest. But then what happens is that ClO radical itself then goes on to react with more ozone to form another Cl radical and 2 oxygens. Not only does it do that, but it also reforms the Cl radical that started this process all over again. And if we cancel this all out, what do we end up with? 2 ozone molecules gets made into 2 oxygen molecules, and we still have the Cl radical that at the beginning started to cause all the trouble. So this can happen many, many times over in a continually downward spiral. So just another cog in the climate change wheel, you think, which is fair enough. And you might think, well, what could be done about this? Well, actually, things have been done about this, and there has been a consensus made and international action taken. In 1989, they were banned under the Montreal Protocol, and generally HFCs are used in their place. This has led to the hole in the ozone layer shrinking and is expected to disappear sometime in the mid of this century. Indeed, this is a hugely successful piece of international legislation, and it proves that international action on climate change issues can be taken when there is communication and agreement. Indeed, with the current state of the world, it can seem difficult to imagine a future in which action is taken upon these issues, but it has happened before, and I believe it will happen again if you are all willing to. Kofi Annan, the ex-secretary of the UN, said perhaps the single most successful international agreement to date has been the Montreal Protocol. He's talking here of all international agreements. That means the most successful international agreement is about the climate. It's about caring for the planet, and it's a model that needs to be used by a generation as inspiration to make change in the world and address the challenges of climate change head on. So, what next? There are no other videos to accompany this or practical work to do, but there are some questions on alkanes that you'll find on Teams. Get used to looking at organic mechanisms as we're going to be developing that skill throughout this unit, although you do not need to draw the mechanisms for the reaction that we've done today. Thanks for joining me again, guys. Please make sure you like, subscribe, and share the channel. And as always, practice makes slightly better.